as compared to the previous lecture. So basically what are matrix converters? They belong to the class of AC to AC converters. So you have direct conversion from three-phase AC or polyphase AC to again polyphase AC at variable voltage and variable frequency. The advantages of matrix converters as compared to classical cycle converters, which are also AC to AC
so we can change frequency. And we can change output voltage. So voltage and the frequency.
Any frequency, irrespective of the frequency of the source. You will do any frequency at the load side, irrespective of the frequency of the source. Now, the circuit shown over here is the circuit of a three-phase to three-phase matrix.
So it is three-phase to three-phase converter.
AC supply available with a fixed frequency and a fixed
So
magnitude.
input is
And
60 hertz
small
and the 2 and the 20
you can attain three-phase
volt.
voltage at any of any magnitude less than
any
the magnitude
amplitude.
of the input, and at any frequency.
Any frequency.
The converter limitation is that the maximum voltage available at the output of the converter is only 86.6% of the input voltage.
So the output maximum is 86.6%.
Anything between 0 to 0.866 times the input can be made available at the output. Now the basic idea behind a matrix converter is that you have three groups of switches.
So you have three groups of
devices.
switches.
You have switches SAA in the first group, which basically samples the input phase capital A at the output phase A.
So there is input,
Switch
small is output.
SBA samples the input phase B at the output phase A, and the third switch SCA samples the input phase C at the output
So
phase
the capital is
Similarly,
input,
A, B,
the
C
small letter is
can also
output.
be sampled
So
at
we
the
have
output
9
phase.
AC
Three
switches.
switches A, SAB, SBB, SCB. Right? And finally, the three input phases can also be sampled at the output phase C, again through three switches SAC, SBC and SCC. So you have a total of 9
So we have
devices.
9 AC switch.
Now this was about
Bidirectional
the
switch.
basic principle of a matrix converter, that any input phase can be brought at any output phase by
So
means
any
of this
input
array
can
of switches,
connect
or
to
matrix of
any
switches,
output.
as you may call it. Let's talk about the switching states of the
So
switch.
switch is state.
Now we know that there are 9 switches.
Nine
and we also know
switches.
that each switch can be on or off.
Each
So for
switch
the
can be
let's
on
talk
or
about
off.
SAA. It can have two possible switching configurations because it can be either on or it can be off. Similarly, SBA will have two switching configurations, SCA will have two switching configurations, so on and so forth. So a total of 2
So total
raised to the power
switching
9,
pattern.
9 times. So a total of 2 raised to the power 9 switching states, which is 512 switching states are possible in this converter.
512.
This is primarily because the converter has a large number
So
of devices.
512.
Therefore, theoretically, it is possible that 512 switching
So it has
states
512.
However, all
switching
of these
states.
500 switching states are
It is
not
too much.
feasible in case of a matrix converter. There are certain switching rules that a matrix converter has to follow. The first switching rule is that
So we have some
cannot
rules.
be given those switching states that can cause the input
So
voltages to
we
be
cannot
shorted.
short circuit input voltage.
It is not possible to, the first rule is that the input phases should not be shorted.
So input cannot be short circuit.
For instance, I switch on SAA as well as SBA, which means that the two lines
So if SAA and then SBA both turn on, then short circuit.
It just happens shorted by
Short
using
circuit.
these two devices. So that's like a dead short circuit condition. It will cause a lot of current to flow through the converter and the
And then
devices
we
will
will damage the two
So this
switches.
condition has to be avoided, which means that in any group at a time only one device has to conduct.
If and
right?
only
so
if
only
one
SPA
switch
or SBA
is
or
turned off,
SCA has to
we
conduct,
cannot
which means
have
that only
more
one
than one
device will
switch.
conduct in each.
Otherwise,
Similarly
the
for
input
B and
voltage
similarly
will
for
be
B.
short circuit.
The second rule is that at least every output phase, if you do, this was about input
For the
phase voltages,
output phase.
every output phase, assuming that we have an inductive load at the output, we cannot interrupt current through
So we cannot
output phase.
open
So output phase
the output
should always
current.
be
Continuous.
connected to some input phase. And in other words, you can say that output phase should not be opened,
So output phase should not be open.
which means that each output phase should definitely be connected to one of these three.
To make
It should be
the
connected
current
only one,
continuous.
but it should definitely be connected to one output phase, otherwise it will be opened. There will be an open circuit condition if I don't keep any of these on, which means that a condition like 0, 0, 0 is not
If
feasible
0, 0,
because
0,
0,
then
0,
output
will not
current is open.
short circuit the input, but it will definitely open circuit the load, and that is not desired because the load is inductive, and sudden open circuiting of inductive loads is inadvisable. So keeping these two switching rules in mind, we know that in every group
Every
only
group,
one switch
if
should
and
conduct,
only
and at
if
least
one
one
switch
should
is
conduct,
turned off,
right?
not
Which brings
more than
us
one,
to the total
not
number of feasible
less than
switching
one.
states in the matrix
So
converter.
in each group, if and only
So
if one switch
only one
is
device should
turned off.
conduct, either SAA or SBA or SCA. So you have a total of 3 switching states possible for this group, a total of 3 switching states possible for the other group, and a total of 3 switching states possible for the third group, which makes
So,
the possibility of
27
switching states. A
27
total of
different
27
states.
switching states are feasible in a matrix
Are
converter,
feasible.
practically feasible in a
Because
matrix
you
converter.
have two
If you
rules.
compare this with a voltage source inverter, there you had
For
in
voltage
each leg
source
you had to
inverter,
make
you have
one device conduct,
eight
and
different
you had to
switching
choose one
For matrix converter,
devices.
you have
In case of a matrix converter,
27
you have to
different
choose one
switching
between 3
methods.
devices every time, right? Therefore, just like in VSI, one device was a node of the other. Here, that is not the case because you have to choose one between 3 devices, right? So, because when you are choosing one device between 2, it automatically means that the other device is a node of the first device. However, here you have to choose one between 3. Therefore, a direct NOT relationship does not exist in a matrix converter, which also makes the modulation or the control of matrix converters slightly more complicated because every time you have to make the choice of
is
choosing
very
a device between
complicated.
3 devices. Also, there are a large number of
27
states,
different
which gives you,
types.
of course, certain advantages, which we will discuss later, but it also makes the modulation or control
The
slightly.
modulation is very complicated.
Now that we know the switching states of the converter, let's talk about the choice of the device. How do we choose
choice
this device?
of the device.
What are the characteristics of this device?
How can you select the
Suppose at any
device?
time we know that in any group only one device will be conducting. Let me assume that this device SBA is conducting, right? Now when SBA is conducting, it means that this potential VB reaches over this point, right? Over the load point, fine? Over the phase A of the load, which means that the voltage across SAA is equal to VA minus VB, right?
VA minus
Which is VAB, the line voltage VAB. Similarly, you can see that every switch, whenever the other switch is conducting, the one that is blocking the voltage will be blocking some line voltage. Each switch is rated to
line
the line
voltage.
voltage, and the line voltage can be positive because it's AC.
But the line voltage
It can be positive
can be
or it
positive
can be
or negative.
Therefore, while choosing the device SAA and also
So the
all
switch
other
should
devices,
be
you have to
bidirectional,
choose a device that
because
has
the
both
voltage
positive
across the
blocking
switch
capability
could be
as well as
positive
negative voltage
and it
blocking
could be
capability.
negative.
Let's talk about the currents to be carried by the device.
Then we discuss
Suppose
about
this
current.
SPA is conducting, and when it is conducting, what will it carry? It will carry the load current. Let's call it IA, small a, right? Now this load current that SPA is carrying, which is the load current in AC current,
So it
of
is
course,
load
because it's an
current.
AC converter.
It is AC current.
Or it can be.
So it could be
So the currents to
positive.
be carried
It
by
could be
devices
negative.
are also positive as
So
well
current
as.
could be positive, could be
Therefore, you
negative.
need a device that has bidirectional voltage blocking
So bidirectional
and bidirectional
voltage,
current carrying.
bidirectional
This
current.
brings us to constructing the bidirectional cell of each device. A very commonly used
So how
topology
can we
is
choose the
IGBTs
device?
with antiviral
Should
diodes
be
in a
AC switch.
configuration.
So how can we
So this is
Okay,
commercially available
then
IGBT
AC
antiparallel
switch.
diode and another IGBT with antiparallel diode
So
such
we
that they
need
are connected
two
back to back
IGBT,
with in
two
complemented
diode.
configuration. It is possible to have other implementations of the bidirectional switch
So this is
such as
bidirectional
the
switch
configuration
or
such
AC
as,
switch.
4 diodes and 1 IGBT.
So we also can use
such
4
as
diode
two
and
anti-blocking
1
and
IGBT.
reverse blocking IGBTs, so on and so forth. So what we know is that for now is that the device can carry
So
currents
the
in both
device
directions,
is
forward
AC
direction
switch.
and
So we have to use
reverse
2
direction,
IGBT,
right?
2
And
diode.
can block both positive
Okay,
voltages as
one
well as
AC
negative
switch.
voltages across it. Now this is about the choice of the device. Moving on to the advantages of this converter. Why should we use this converter? Classically, I mean, it's not a very popularly used converter because of certain disadvantages also and certain complications or complexities in its operation. But what are the advantages? Why
So what are the
such a converter
advantages
being used?
of
Generally, if you want to do
AC to
AC
AC
conversion,
matrix
you first
converter?
convert AC into DC and then again through a rectifier and then you use a
We
DC
also can
capacitor,
use
and then
AC
you
to
again
DC
convert it into
and then DC to
into
AC.
three-phase AC to an inverter. The advantage of using a matrix converter over the two-stage AC-DC AC conversion is one, that the converter is inherently bidirectional. It uses bidirectional
Bidirectional.
devices, which
So this
means
is
that
first
energy cannot only
advantage.
flow
The
from this
energy
side to
could
this side,
be
but it can also
bidirectional.
flow from the load side to the source side. So the load and source are interchangeable. Energy flow is bidirectional. If you're using a
So the
motor drive,
energy
it's
flow
very easy
is
to differentiate the
bidirectional.
generation of the drive using a matrix converter. The second advantage of using matrix converter is that they are very compact in size.
Compact in size.
The reason that they are very compact in size is because when you eliminate the DC stage, you also eliminate the DC link
So you can remove
DC
the
link capacitors,
DC link
passives, like capacitor
capacitor.
conductors are known to
So we don't
occupy
need
a lot of space,
DC
or
link
they have a large
capacitor.
footprint, or they contribute to a large volume, large size.
So then we
But
can
when you're
reduce the
eliminating
size.
capacitor, in the DC link, you just have silicon, IGBTs or whatever devices.
We only
you use,
have
you only
silicon
power electrodes, that's power
device,
electronics
but a
solution.
non-capacitor.
Only switches that are converting AC to AC, so it will be a very compact, small
very
size,
compact and a small
setup as
size.
compared to an AC converter. Not only will it be compact, but it will also be more reliable. There have
Reliable.
been studies that have been done to compare the reliability of matrix converter with AC-DC AC converters. The reason it is more reliable is because the DC link capacitors used in AC-DC AC converters, they are known to have high failure rates or
So
high
5 years,
probability of
you have to
failing.
replace
As a result, when one
the
component
DC link
fails, that is
capacitor.
the capacitor,
But now you can
it has to
remove
be shut
DC
down
link
and
capacitor.
replace the DC
So
capacitor.
you can save
It's a
money.
matrix converter because you do not have anything like an electrolytic capacitor. Therefore, its reliability is higher, especially
reliability
as our
is better.
device technology is improving. Matrix converters have more scope in the future because they are
So,
more focused on power
in the
electronics,
future, it
pure
has
power electronics,
opportunity.
more silicon solutions as compared to AC-DC AC converters.
Compared
which
to
also have some
AC/DC AC.
passive components. The third advantage of using
So the
matrix
third
converters is that
advantage,
they offer improved power quality on the source
Power
as
quality.
on the load
So
as
the
well as the
input
baseline,
current
which means not only
and
are
the
the
input
load
power
sinusoidal,
factor
but it is
is very
also
good.
possible to
Input
ensure
current
that the
is
source
sinusoidal
current, that's the current
and the
generated
power
by the
factor
grid,
is
they are
1.0.
also sinusoidal in nature. Of course, source, then you need sinusoidal grid current.
So
You also need a
sinusoidal
small
current
filter
and
input over here.
very good power factor.
Which will be a very small sized filter, which will help you in achieving sinusoidal grid currents.
So you can get sinusoidal currents.
Advantage. And that is improved power quality on the grid side, load side, as well as the grid side.
Include unity power factor and the sinusoidal current.
Matrix converters is that you have a completely controllable power factor. So even
So you can control the
maybe
power
something like an
factor.
induction motor that is drawing reactive power from the system, but somehow you can control the switches in such a manner
So you can
that
control the switch
grid does not
to
see that
control the
reactive
power
power is
factor.
being drawn. So it will you can operate it at unity power factor.
Unity power
Use it
factor.
like a compensator which is
So
drawing
you don't need
loads from the system
power factor
and
correction
compensating
circuit.
other lags in this lagging loads in the system. So the power factor of the currents
Power
drawn from the
factor
grid can be
can be
limited, it can
controlled.
be leading, it can be lagging. It is basically completely controllable.
Completely
power factor.
controllable. Okay, you can control power factor.
There are some other advantages that have been explored recently, that is a possibility to eliminate common mode voltage, but I think discussing that would make this lecture too long, so we can stick to the basic advantages that are known of this converter. Now, the next thing that I would like to discuss with you is a brief introduction to space vector modulation.
Space vector modulation. How can we do the
Now, I already
space
discussed
vector
whenever we do
modulation
space vector
for the
modulation, the first
matrix
thing
converter?
is to draft or just sit down and write all the possible switching states of the converter, which we have already discussed that there are 27 in number.
27
states.
different
Now, what are those
switching
27
patterns.
switching states? Suppose the first group of states that we have are states that sample this at two output phases, they sample the same input phase, and at the third output phase they sample some unique input phase. Let me explain. For instance, a state like A, B.
So A, B.
over here means that at output phase A you have input phase A, at output phase B you have input phase A, and at output phase C you have input phase B. The capital letters are representing the input phases,
So capital
which occur
letter is
at the
input.
output phases A, B and C, right? Similarly, another such state, similar state is A, B, A, B, A, or you can also have B, B, A, B, A, B, or you can also have A, B, B, which means two A's and one B, which are the top three states, or two B's and one A. Similarly, you can have B and C, two B's and one C, or two C's and one B.
So this is
Similarly,
a
you can
possible
have
switching state.
two A's and one C, or you can have two C's and one A.
So you can see a lot
If
of
you just add up all the
combinations.
states, it's 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. A total of 18 switching states,
So
right?
18
Where?
switching state.
Two same input phases and one
Same
different
input
input phase
and
are
one
sampled
different.
output. So these are the main 18 states. Now we are
So
left
18
with
switching
27 minus 18, that is 9 switching states. These are the main 18 or active vectors, you can call them.
This
You
is
also have
active.
0 states.
We have zero
Zero
state.
states are one in which the same input phase is
So
sampled
AAA,
at the out.
then it is
or
isolated.
at the out.
Then we
Or
call it
CCC.
is zero voltage.
Obviously, in this case, the output line voltages will be zero because line voltage is what? VA minus VB, that
So
is
they
A
have
minus
the
A,
same
that is 0.
voltage.
Or VBC is
So the
also
output
A minus A or
voltage
B minus
is
B or
always
C minus
0.
or 0, and VCA is also 0. So these are the 0 states.
So we call zero state.
Now, these
Zero
18
voltage
plus
state.
these 3, that is a total of 21.
So 3
Most
zero
of the time
voltage.
you see that when you
18
are implementing space vector
active
modulation,
voltage.
you use only these
So
states.
now we have 21.
Apart from these 21 states, there are some more states called 6 rotating vectors, which are also used sometimes. They have their own set of advantages, but most of the time they are not used, and I will also discuss why they are not used. These states, 6 states, are those states that switch a unique input phase at the output,
So
which means
unique
something like
input.
A, B, C,
So all of
and
them are
output phase is
different.
ABC, or B, C, A,
All of
or
them are different.
C, B, A, or A, C, B, or B, A, C, or C, A, B. So
So
these
all
6
of them
states,
are
1, 2,
different.
3,
So
4,
they
5,
have
6,
unique
these 6
input.
states are also switched sometimes, but most of the time they are discarded because they result in a rotating space phasor, which I will discuss with you. So let's try to construct the space vector diagram, the line-to-line voltage space vector diagram, right? Now I'll retain only 3 states because I can't repeat the space vector analysis for all the 18. You can do it as a home assignment.
Total
But
is
these 3 states I will
27.
retain. Only the
21
top states
plus
of,
3 plus 6
the 18
is
vectors. The
27.
0 vectors, I know they will result in a position at the origin because the line voltages are all 0, so I can delete them, right?
Okay.
Let's try to construct the space vector diagram for the first 18 states, out of which we have retained only the top 3 states. Now the space vector of the line voltage.
So now we
space
discuss
vector is
about
two by
the
three.
space
Output line
vector.
voltage, VA,
Space vector
at
modulation.
plus the output line voltage VBC at an angle of 120 degrees plus the output line voltage VCA. Please remember the small alphabets ABC represent the output phases and the capital alphabets ABC represent the input phases. Minus 120, right? For this particular state, that is AAB, the space vector can be computed. The space vector is AB is 0 because A minus A, that is simply 0 at an angle of 0, whatever it is, completely 0. VBC is actually input line voltage VAB.
VBC is V.
The output line
AB.
voltage VBC at this time when you switch the state will be the input line voltage equal to the input line voltage VAB at an angle of 120 degrees, right? Plus VCA, it is VBA.
So VBA.
VA at an angle of minus 120 degrees. I can write VBA as
AAB.
minus
So we can obtain the voltage vector like
If I
this.
solve this, I get 2 by 3 into root 3 VAB at an angle of 90 degrees, right? So, assuming that this is some constant, let's call it K, the space vector corresponding to this switching state is K times VAB, input voltage VAB at an angle of 90 degrees. Similarly, I can find the space vector for this particular state and it turns out to be K times, again VAB because we're only using A and B vectors, at an angle of minus 30 degrees. And if I find it for this third state, it is again K times VAB at an angle of minus 150 degrees. You can do it yourself and find the space vectors. So we are currently doing it only for 3 switching states. Now, the output voltage space vector, the output line to line space
Output
vector,
voltage.
is a function of the input line voltage VAB, and if you use the other states, it will be a function of VBC also, a function of VCA also, so on and so forth. Because please remember, right now we have found the space vector of only 3 out of 18 switching states, right? So if I I want to draw the output space vector diagram, if I check the input phase voltages, input phase voltages are line voltages, they are VAB. At 120 degrees lagging, there will be another phase voltage VBC, and then there will be another phase voltage VCA, right? So there will be 3 phase voltages, each
So
one
we have 3
apart.
phase voltage.
And if I'm trying to construct the space vector diagram of the output phase voltages for this particular state, it will be VAB at an angle of 90 degrees. So it will be measured with respect to VAB, but it will be at an angle of 90 degrees, and of course scaled by a factor of K, which is 2 by 3 into root 3. So this
This is the first one.
The first state is giving me this vector.
So this is the
But
first one.
the first state is a function of VAB, and VAB might be positive or VAB might be negative. And when VAB is negative, it will actually give me a line along this, right? So this particular state, AAB, is going to give me a space vector position along this line, either positive or negative. In case of a BSI or in case of a multi-level converter, the input was always VDC. It was always fixed. The input was not changing polarity. But in case of a matrix converter, the input is changing polarity, and as a result of that, whichever state is a function of that input, that state will also result in a space vector that will change polarity, right? So this particular state will give me a space vector diagram like this.
VAB could be positive.
Now the second state,
And the VAB could be
the
negative.
second state, it is VAB at an angle of minus 30. So VAB at an angle of minus 30 is something like
Delay 30 degrees.
this.
Delay 30 degrees.
It is VAB at an angle of minus 30. But again, VAB at an angle of minus 30, whenever VAB is negative, it will give me
So it could
something
be positive.
like
It
this.
could be negative.
The third state is VAB at an angle of minus 150. So VAB at an angle of minus 150 is something like
Minus
this.
150.
But when VAB is negative, it will be along the
So it
opposite
could
side.
be positive or negative.
That means 3 states.
So we have
are
3
making-
states.
are making a hexagon for me.
So we have 3
This is
states.
that hexagon. I'm talking about the line voltage space vector diagram, and this is the hexagon of the line voltage space vectors, right? Now, one state is occupying this line, one state is occupying this whole line, and one state is occupying this whole line. How many states are still left? 18 minus 3, that is 15, right? And when I check them, they will also be functions of, might be functions of VBC or VCA at some angle, of course, but they will also occupy the same lines, right? So there are a total of 3 lines, each having 2 positions. That is a total of 6 positions, but each line will be occupied by 6 states. 6 into 3 is a total of 18. If you reconstruct for every state, you take up every state and you find out its space vector, you will see that they occupy the same lines. That means the same output is produced by 6 states in a matrix converter. So there is redundancy depending upon whether that time VAB is positive. These 6 states may occupy either this point or they may occupy either this point. Or it is also possible that some of them may occupy this point and some of them may occupy this point, right? But the point is that 6 states occupy this line, 6 occupy this line, and 6 occupy this line. Unlike a multi-level converter, you do not have too many positions on the space vector. You have the same 6 positions like that of a VSI, but there is redundancy. That means more number of states are occupying the same positions. So it has, it is different from a multi-level converter in the sense that it does not occupy large vectors and medium vectors and small vectors. It occupies the same position, but there are too many
Occupies the
states
same
that give you
origin.
the same position. And it is this redundancy which is actually helpful in making the matrix converter an advantageous converter over voltage source inverter, because just like you have a space vector diagram of the voltage source inverter, you will also have of the load voltages of the converter, you will also have a space vector diagram of the source currents of the of the converter. The source currents will be a function of the, just like the load voltages are a function of the source voltages, similarly the source currents I capital A, I capital B, I capital C will be a function of the load currents IA, IB, IB because of some state, similarly IAAA in case of zero states, or IBBP in case of zero states. And you can also construct a space vector diagram of the source currents of the matrix converter. So you will have another, space vector diagram constructed.
We also have current.
You have
So
two space
current.
vectors running parallelly, right? And then you, whatever source current is desired, sinusoidal source current, you will check that source current, whichever sector it is lying in. There will be 6 states contributing to this vector, and you want particular voltage in this sector. You will combine the two informations. You will see which state. There are multiple states giving you this position. You want this position on the current space vector diagram, and then there are multiple switching states giving you this position which you want in the space vector diagram of the voltage, because you're simultaneously controlling the source currents and the load voltages. Now there are 6 states giving you your best source current, and there are 6 states giving you your best load voltages. You will switch that state which is common to these two, which is giving you the best of both the worlds. This redundancy basically helps you in in controlling both source current and load voltage together. So parallelly both the space vector diagrams.
So you have to
I'm not
control
going to
input
detail
current
because it will get too complicated.
and also output
For you.
voltage.
But if anyone
So
is
it
interested in its
become
implementation,
more
of course
complicated.
we can sit together and discuss how it is to be done. What my basic point is that in case of matrix converters, because you have redundancy associated
You
with
have
each state,
redundancy.
with each space vector position, and we use that redundancy to control source currents as well as
You have to
load voltages
control source current
simultaneously.
and the output
So that
load
is about,
voltage.
the space vector of the
This is space vector.
implementation of the matrix converter. Now, I also want to talk about the nature of the converter.
The nature
So the input
of the
voltages
matrix
are
converter.
sinusoids, if you want to
So
see the
input is sinusoidal voltage.
The line voltages will be something like this. What basically happens in a matrix converter is that we try to switch the input voltages at the output such that the fictitious rectified envelope, whenever
So we
some
have
line
to
voltage is
control
at its peak, we
the
try
input
to raise that
voltage.
particular line voltage at the output, and it becomes a PWM signal sampling this output, something
So
like
output
this,
is like
at any
this.
frequency that we want from the load.
So output is like this.
And once a load voltage waveform like this is achieved, load currents will become sinusoidal, 3-phase load currents.
And the load
Then
current
we
is
also
sinusoidal.
consider them. Then these sinusoidal load currents, of course if it's an RL load, these sinusoidal load currents are sampled at the input to give us discrete source currents,
So input current is like this.
which are again controllable. So load voltage, V0,
This is
is
load
a controllable
voltage.
switching function of Vs.
This is
And
input
source
current.
current Is is a
Yeah.
controllable switching function of I0. And because the source current is discrete, it has higher order harmonics.
So we
therefore
have
you
higher
always get
order
a small
harmonics
LC
in the
filter at the
input.
of the converter.
So we have to
Each phase.
design
So
LC
that you
filter.
can convert this sinusoidal
To
waveform
remove
and
the
its discrete
harmonics.
waveform into a sine wave.
To
Right?
obtain
This is
sine
about the
wave.
nature of
Sinusoidal
the load voltage
current.
and the source current of matrix converter. Now, even though the matrix converter offers so many advantages like improved power quality,
Improved
control
power
power
quality,
factor, bidirectional power flow, and
Controllable
it's also
power
compact in
factor,
size,
bidirectional power flow, very
then why
compact,
is it not so popular in case
not
of
popular. Why
in
not
industries
popular?
or in practical implementations.
In
There are many
industry.
problems associated with matrix converters, and
What
one
is
of
the
these
problem?
problems, which is now solved, is the commutation problem.
Commutation
I will
problem.
discuss this briefly with you.
So we
Because
discuss commutation problem.
commutation is a big issue
A
when
big
we talk
issue.
about four-quadrant switches
Okay,
or
if you
bidirectional
study
switches.
matrix
Using
converter,
this
the
bidirectional
communication
switch,
is
which
a
I
big
showed,
issue.
that is a basic switching cell of
It's
matrix
important.
converter. Even if you're using it in some other converter, you are bound to face a commutation problem. Now, what is a commutation problem?
What is
Let's take
commutation problem?
the group 1 of matrix converter, the first three switches. The first switch samples input phase A. These are in common emitter configuration. They switch phase A at the output phase A, and then they also have anti-parallel diodes.
So
like
we
this.
have input A and output A.
So you have something like this, and then there is another switch that switches phase B,
So we have switch
the
B.
output of the matrix converter. The same phase A. You will similarly have phase C in group A, and they
You
also
have
will
C.
the same output.
So we have A and B.
Now, what is commutation? I'll talk
But
about
all
only
of
suppose you
them
have to
will
transfer
connect
from
to
this switch to
AP's
this switch.
output.
You can also transfer it from this switch to the C switch.
No,
but I'm not
we want
talking
to
about it right
transfer
now. I'm
from
just
A to
assuming
B.
transfer from this switch to this switch. Commutation is nothing but transfer of current. One switch cell turning off and the other turning on.
So
So current
one
is transferred.
is
This
turned
phase A
off,
current is
another is
transferred
turned
from this
off.
switch to
So we
this
want to switch from A to
now,
B.
suppose, let's call this switch as S. Of course, it's SAA, and this is SBA. And we assume that their gates are tied. That means the same switching pulse is given to both the IGBTs of the common switch cell, and the same switching cell is given, the same pulse is given to both the devices of SBA. Let's assume that SAA goes off and immediately SBA goes on,
So
right?
SAA go off
SAA
and
and this
SBA
is
go on.
SBA, and immediately it has gone on.
We want to transfer
Which
from
means
A to B.
that SA will take some time to turn off,
So sometimes we turn
and
off.
SA will have lesser turn on time because turn on times are lesser
So
than
we
turn
have
on
delay
times.
time.
And there will be a small
Then they
interval
overlap.
where both of these will be on, which will cause cause a short circuit of the source of the line voltage. ये
Because
भी
they have
on
delay
so
time.
something like this, current will flow like this, and the source will be short circuited.
So short circuit.
वोल्टेज सोर्स इन्वर्टर्स ऑल्सो दिस प्रॉब्लम इज एनकाउंटर्ड कि आपकी एक डीसी बस होती है और दो कॉम्प्लीमेंट्री स्विचेस ऑन अगर साइमल्टेनियसली हो गए तो आपकी डीसी बस शॉर्ट हो जाती है. In that case, what we generally do is that we give a small dead band,
So we get dead time. Okay.
right? And I've already discussed it. We give a small dead band कि एक switch on हो गया, and then after some
We have
time
to
the other
wait.
switch is turned on, so that we can ensure that this switch has turned off
Totally off.
safely,
Then we turn
and
on.
then we turn on the other switch, right? So you avoid any short
So we
circuit.
call this is dead time.
In case of a voltage source inverter, a dead band is given, or you can say you deliberately create an open circuit condition. And in this open circuit condition, it is also possible that during some time, SA has turned off completely and SA has
So
not been turned
SA
off.
should
That
be
means it's an open circuit
turned off
condition. The
completely.
load current उस time पे
Then
कहाँ
we
से
can
जाएगी?
turn
There
off
are
the
anti-parallel diodes, right? In a voltage source inverter. अगर लोड करंट आपकी पॉजिटिव है तो वो यहाँ से जाएगी, और अगर लोड करंट आपकी नेगेटिव है तो यहाँ से इस ऊपर वाले डायोड से जाएगी. Which means voltage source inverters have freewheeling paths.
Free feeling
Even if it is
dead.
an open circuit condition,
So they
momentary
have
open
free
circuit
feeling
condition
dead.
in the load. But in case of a matrix converter, if I go for dead band based commutation, that means giving a small delay between the two pulses, what happens in the open circuit? Neither this is on, neither this is. दोनों में से किसी के पास pulse नहीं है. अगर current positive है तो वो कहाँ से जाएगी? The diodes are not connected that they can carry any current. They're connected back to back. You need the current path to be through a switch. So there is no freewheeling path.
So
in
we
the
have no
bidirectional switch.
free
Is
feeling
it possible
diode.
that any current will be carried by the diodes? No, because
No
the diode
free-wheeling
always needs
diode.
one switch to complete the path. This diode needs this switch and this diode needs this switch. And when there is no pulse to any of the two switches, it will not conduct. The diode cannot conduct alone. So the absence of freewheeling path in
do not have
this
any
converter or any
freewheeling
bidirectional switch used in any converter for that matter causes a commutation problem.
So cause
You cannot give pulses
communication
next
problem.
to each other, immediately next to each other, because you know that it will cause a short circuit.
So
you cannot
you
go
will
for
cause
deadband-based
short circuit.
commutation, delay-based commutation, because you know there is not a freewheeling path. The load current does not have a continuity, will get broken if you give a delay in current, and because of that break in continuity, an LDI by TT kick will be
So
induced
the
and
LDIDT
it will damage your switch.
and we will create a spike.
This was one of the
to
biggest
damage the
challenges
switch.
in matrix converters, and when this challenge was solved, I think you can say the biggest problem of matrix converters got solved. And in the future also, it is expected for various applications like electric vehicles and
But
especially
electrical
electric
vehicles,
you are going to use these as the bidirectional switch cells. If
Bidirectional
not as a matrix
switch.
converter topology, even in DC to DC topologies or AC to DC topologies, it is possible to use this switch cell
it is
because
a
of
new
the advantages
device.
that it offers. But whenever you have to deal with such switch cell, you have to take care of the commutation.
Communication.
So how do you basically
communication
communicate
problem.
such devices? How do you transfer current from this switch
So
to
how
this
can we
switch?
transfer
The key
from A
is
to B?
that you give separate pulses to all the four devices. You don't treat them exactly like these two, like one switch, but you treat them as two switches, especially during the transfer of
So
current.
during the
When
transfer,
they are
you have
conducting,
to
you give suppose
treat
this is
as two
continuously
different
conducting, you
switches.
can give the same pulse. But when you have to transfer current from this to this, you have to give a different sequence of pulses to all the four devices. So now I will call this one as SAA plus, because this device is going to conduct the positive A current, and this one I am going to call as SAA minus, because this one is going to conduct the negative phase A current. Similarly, this is SBA plus and this is SBA minus, because this one carries a positive current
One
and this one
positive,
carries the
another is
negative
negative.
current, right? Now you have four devices
So we
instead
have
of
four
two
devices.
in terms of gating. And what my goal is to transfer current
So we have to transfer
From-
current from A to B.
these devices to these devices, which means that initially both these devices are on. So my state is 1, 1, 1 and 1, right? And I have, 1, 1, 0, 0, because these are off. And I have to eventually reach a state where both of these are off, 0, 0, 1, 1. And this commutation process, I have to do this in 4 steps to ensure
we have
that
to
neither there's a
finish
short circuit
in
nor
4
there is
steps.
an open circuit.
To
But
transfer
for
from
four-step
A to
commutation to
B.
take place, this multi-step commutation is
So we call four-step commutation.
voltage-based commutation. But
Four-step
four-step current
commutation.
commutation is the most commonly used commutation. It's considered to be amongst the safest, right? So I will basically do one thing. I will measure the load current and I will
So
sense
we have
its direction.
to measure the load
current
current.
is positive. Then
If the current is
I know that
positive,
initially the pulse is going to both SAA plus and SAA minus, but I also know that if the current is positive, then SAA plus is conducting.
so
So the first thing
SAA
I
plus
will do
is
is
turned
that
off.
I will turn off SAA minus. Okay? So this is SAA plus, this is SAA minus, this is SBA plus, and this is SBA minus. I will turn off SAA minus because I know it's positive current. This
Now
combination
we know
is
it is
positive.
positive current.
Similarly, this
So
is
it should
combination
be
for negative current.
SAA turned off.
So I will
And
check
the
that the
SAA
current is
minus
positive. So
turn
SAA minus is anyway not conducting. So my first step is to turn off SAA minus.
So we turn off
these are
SAA plus.
right? Then I also know that the current IA is positive, which means
So
in the
current
next
IA
set of
is
devices, SBA plus has to conduct because the current is positive,
So
right?
current is
So I will
positive.
switch on SBA.
So
and
SBA
minus,
plus
SBA
is
plus and
turned off.
SBA minus को off ही रहने देते हैं. So this is my second step, right?
So second step.
Now the third step, अब इस case में if you check the latest step 1010, SAA plus and SBA plus are both on.
So
But
both
they don't
of them
cause
are
short
turned off.
circuit.
They
Because
share
by nature,
the
these
current.
are in common cathode configuration, or you can
They
say
share the
common
current
point.
because SAA plus and the SPA plus are both turn off.
forward bias will draw, depending upon whether phase A is at a higher potential or phase B is at a higher potential. Naturally, जिसका forward bias ज़्यादा होगा, इन दोनों में से वही एक conduct करने वाला है, right? So there's not going to be a short circuit condition.
So no short
शॉर्ट सर्किट कंडीशन तब होने का खतरा था अगर आप इस वाले को ऑन कर देते तो ये एक रिटर्न पाथ दे देता वापस शॉर्ट सर्किट के, बट दिस एंड दिस ओनली वन विल कंडक्ट बाय डिफॉल्ट. नाउ आफ्टर दैट I will do one thing, I will turn off SAA plus because eventually my goal is to turn it off. This has already been turned off, this has already been turned on, and this remains 0. And finally I reach my final goal, that is turning the other last switch also, SPA minus also on, so that whenever the current becomes negative, this will take over the current as well. So this happens in 4 steps.
So
1,
we have
2,
1, 2, 3, 4.
current
Step.
commutation from 1100 to 0011
To finish
has taken place
the
in 4
commutation.
steps, and I have ensured that neither of
Then we can
short
search
circuit
for
will occur nor
the current
open
from
circuit will occur. So I am
A
ensuring
to
safe
PA.
commutation. Similarly for negative IA, there will be another sequence, and I'm sure you should be able to do that negative sequence itself. So when 4-step commutation, I think it was
So
given
we
in the
spend
year
the 4 step
1991
to finish
in a conference paper by
the
a person called
commutation.
Bulani.
So this is 1990.
And it
People
really changed the
oppose
way matrix
this
converters
idea.
are looked upon, because
And then he
commutation
get a
according
paper,
to matrix
he
converters
graduate
was a very big problem,
because this
because
is
it
a
was dangerous for
big
the
issue.
converter. These converters were not reliable because they
To
were
make sure
provided with extra protections
the
through
safety of the matrix converter.
circuits, because the commutation was not safe. There were high commutating voltages involved, LDI by dt kicks involved in
So
the
we can
commutation.
pause
And then,
LDIDT.
once this commutation problem was solved through 4-step commutation,
4-step
it has
commutation.
become more easier to implement bidirectional switches in such circuits. So I decided that I'll also be
So
able to
commutation
have
is
4-step
important.
You may not use
4-step
matrix converters. It's
commutation.
very likely that the future will be based on bidirectional 4-quadrant switches, and you must know that how these 4-quadrant switches are commutated, how they are turned off and how they are turned on.
So how they turn
And,
off,
that is
how they
about
turn on.
4-step commutation and matrix converters. There's a it's a huge area where a lot of things can
It
be
is a
discussed.
huge
I've
area
shortlisted
and
some
a lot
basic
of
things
things.
which I felt you should.
So it is a big
just
issue
know
for
what's
research.
converter or its functioning. We can always have discussions on that. So that is all for today. We have a last lecture after this on Z-source converters, and with that our syllabus will be over. I wish you all the best for the upcoming exams, and take care, stay safe.
Okay, so we can have 20 minutes break and